Hello and welcome. The purpose of this video is to go over the standard entropy change as well as the Gibbs free energy calculations that we saw during high-level time on entropy and spontaneity. All right, so we've already studied lots of different standard energies and enthalpies. We've looked at some of these in core time, and we've looked at like bond dissociation. We've looked at some of these in HL time. So entropy change, remember entropy is the disorder of the universe. And you can look at the disorder of any particular thing you're interested in. So you might look at a chemical reaction, you might look at a physical change. And at the beginning of class, we talked about if enthalpy changes are positive or negative based on if order is increasing or if disorder is decreasing. So for example, melting, I go from solid to liquid, I'm becoming more disordered, positive entropy change. Great. We can quantify this. We can quantify this using standard entropy values. So, for example, I have here the standard entropy value for C4H8. C4H8, hopefully you're saying to yourself, butene, some isomer of butene, right? CnH2n. What does this number mean? Well, this means this is the change in entropy. This is the change in entropy when 1 mole of C4H8 is heated from absolute zero to the thermodynamic standard temperature of 298 K. So change in entropy when 1 mole of C4H8 is heated from 0K to 298 K. And we have here the standard entropy values for C4H8, H2O, C4H9OH. So if I were to write, for example, these kind of intermediates in the same way that we did with Hess's law, you wouldn't have to write out entropy changes in reactions. That would be kind of a weird thing to think about, but if it's helpful to relate it to what we did before, well, at 0 Kelvin, obviously C4H8 would be a solid. So to C4H8 liquid, 298 Kelvin. All right, we would never actually write this out, but if this is kind of a helpful way to conceptualize what we're doing right now with what we did before. This is very similar to what we saw with, and maybe it's not on this list, but with enthalpy of combustion and enthalpy of formation. All right, so I am trying to find the entropy change for this reaction. So I'm going to use the standard entropies of each of these. And in this case, do I use the standard enthalpies and reverse the sign for my reactant or my product? Well, think about what the process shows. In the process that each of these would go through to find standard entropy values, the thing I'm interested in is at the end. That means my reactants in my equation, those are the things I'm going to have to reverse the sign for. So what would this look like? Well, I have here my reaction, I have my standard entropy values, my coefficients are 1 in this case, so I don't need to worry about that. And to find the standard entropy for this reaction, I merely take the sum of the entropies for the products, which is in this case is just 228. I flip the sign in the reactants, which you see here, I flip the sign, and then I add the entropies here and here. And I get negative 271 joules per Kelvin per mole. And this is indeed entropy units. Negative sign. We could have predicted, even before we did any of these calculations, we could have predicted that this would be negative because I have a gas going to no gas. So I expected that entropy was decreasing and becoming less disordered. So this first calculation, really just putting a value on those initial things that we did way at the beginning of class when we looked at if processes had positive or negative entropy changes. All right, the other math that we saw right at the end of class today was, of course, Gibbs free energy. So change in free energy. Someone at the end of class stopped and asked, what are the units? Well, if I have energy, my unit should be joules or kilojoules. When 1 mole of a compound is formed from its elements in their standard states under standard conditions. So kind of like enthalpy of formation, but this time we're worried about change in free energy, not change in enthalpy. So again, you can use this to find the Gibbs free energy for an entire equation. I can take the Gibbs free energy for C2H5OH, and remember, where in Gibbs free energy we're worried about 1 mole of a compound being formed. So that would be, for example, here, this number represents the change in Gibbs free energy, the change in free energy when 2 C's plus, let's see, H5, plus 5 halves H2, is that what I want? Plus, sorry about this. Thanks for bearing with me here. Okay, 2C plus 3H2 plus 1/2 O2 yields C2H5OH. Notice this must be 1 by definition, which is why I was using half coefficients. So it's the change, this number again, is the change in free energy. Change in free energy. It looks very similar to enthalpy of formation, but in this case, we're not looking at enthalpy or just enthalpy. We're looking at the change in free energy, and we know free energy comes from enthalpy plus temperature times entropy. So free energy is a little bit more complicated than just the enthalpy. So the thing we're interested in, the thing in our reaction is going to be in the products of my intermediate. That means that in my products, I'm going to be in the right direction. In my reactants, I'll need to switch directions. So you can find these in section 12 of the data booklet, just FYI. And we see here how we would set this up. So C2H4, I have my free energy H2O, I have my free energy C2H5OH, and I have my products C2H5OH minus change signs in the reactants. And then again, I just had coefficients of 1 here, so I didn't need to do any multiplying. I just add the delta G's for each of my reactants. If you did have a coefficient, you would multiply these by your coefficient. This is the math we need to do in order to figure out if a reaction is spontaneous or not. And this reaction would indeed be spontaneous because negative delta G means the reaction is spontaneous. All right, I hope that helped. As always, let me know what questions you have. Thanks for watching.